Welcome everyone to the third experiment in general physics, which is Newton's second law. Up to now, we have mostly dealt with kinematics, which is a way to explain how the motion happens. But after this point, we need to explain the dynamics. That's why we need to explain why the motion happens. And in order to do that, we are going to need to have a deep understanding of Newton's law. The first law of motion is mostly called the law of inertia. First law of motion. It says that basically an object in constant motion will stay in that motion, and or an object in rest will stay in rest unless acted upon by force. If we try to explain it mathematically, we can write that if the total force is 0, then the object's velocity will remain constant, or it will be 0. Or basically we can say that the velocity will not change, so we can write the change in velocity will be equal to 0. Now this attribute is usually attributed to the inert property of an object, which is called inertia. We can write it like that, inertia, and it is defined as the resistance of an object to the change in its motion. So let me write it, the resistance an object to a change in its motion. The way we experience inertia in our real life, if you are on a bus that's going with constant velocity and then the driver sees the red lights and hits the brake, at that moment you feel like there is a force pushing you forwards, but in actual reality there is no force. It's your inertia resisting that change in your motion, so that you feel like you are being pushed forwards. So how do we measure inertia? Actually, we measure inertia by measuring an object's mass. So if an object is heavier, it will be harder to force it into motion. If it's a light object, then it will be easier to make it move. And which brings us to the second law of motion, which is what we are going to be trying to prove today. Motion, which is explained by the famous equation that says the net force is equal to m times a, which basically says that given a force will cause a change in motion. Acceleration is defined by the change in motion is defined as the change in motion. So a net force will cause a change in motion, and the mass will resist that change in motion. And then there is the third law, which is generally known by the action-reaction principle. Third law of motion. It basically says that for every action, there must be a reaction which is equal in magnitude, but opposite in direction. The most common place where we see a reactionary force is what we call a normal force. Let's imagine there is an object sitting on the ground with mass m. What happens is the gravitational force will pull this object down with a force which is equal to m times g, which we call usually Fg, the gravitational force. And this means that this object will exert a force on the ground which is equal to Fg. As a result, the ground will push the object upwards, and it will be the same force, we call it F normal, which will be equal to, let me get a, which will be equal to the gravitational force in magnitude, but will be opposite in direction, which will be m times g. Of course, I have to put a minus sign here because it will be opposite. Now, our aim today is to verify Newton's second law, is to prove Newton's second law. The way we are going to do that, generally I like to write the equation as like this. The acceleration is equal to the force over the mass. Acceleration is directly proportional to the force, and it is inversely proportional to the mass. So what I'm going to do is, I'm going to set up an experiment, and I'm going to first verify this acceleration is proportional to the force by keeping the mass value constant. And then in the second part of the experiment, I'm going to keep the force constant, and I'm going to see how acceleration changes with respect to the mass. And my setup is sort of something like this. I'm going to have a mass here, which is tied to another mass on the side of the table like this. There is a setup here. Now what you see here is the setup of our experiment. Let me just quickly introduce the equipments for you. I have here an air supply, which when I turn on will supply some air onto this air track here, and because of that air coming out of these holes, this glider will not experience will experience less friction, which will help me with get some good results. I have here a photo gate setup. There's the main equipment is here, and the secondary photo gate is here, which will help me determine, which will help me make time measurements. And the way I'm going to use this time measurement is as follows. I'm going to measure the velocity of the glider at 2 points. First here, and then secondly here, which will help me determine the change in velocity. And then I'm going to run the same experiment again, starting from the same starting point, because I want the motion to be same. And then in the second run, I will measure how long does it take for the glider to reach from this point to this point. So I will have the time it takes for that velocity change. Therefore, I will use the principle of average acceleration, which is the change in velocity divided by the time it takes for that change, and which will help me measure the acceleration of the glider. And the velocities will be used by using the gate mode of this photo gate. The way it works is, if I put this on gate mode, what it does, as soon as this signal is interrupted, it will start measuring, taking a time measurement, and then the moment the signal comes back, it will stop the measurement. Now what it does is, if I just take this flag off for a second, the way I'm going to measure velocity by using the gate mode is using these flags, which is the one I have on my hand is identical to the one on the glider, and this the length of this flag is 10 centimeters. And if I use the gate mode and take a time measurement like this, what it will do, it will measure the time it takes for glider to travel 10 centimeters from this end to this end. So I can use that to determine the velocity. And the way I'm going to measure the time it takes from for glider to reach from this point to this point is by using the pulse mode. And the way pulse mode works is it starts taking measurements as soon as the signal is interrupted from here, and then it stops the measurement as soon as the signal is interrupted at this point. So it will tell me how long does it take from this point to this point, and then by making 2 runs starting from the same position, because I want the motion to be the same in each position, I will have all of the measurements I need. And here I have some masses which I'm going to put on this glider, which will help me with the change the mass of the object. And here I have also a mass hanged here, so I will change the mass, the force, by changing the mass here. So in the first part of our experiment, what we were going to do is to measure the effects of changing the force on the acceleration of the object itself. So I will reset all of these equipments, and here on the mass hang I put 10 grams here, and on my glider I put my masses on the glider here, 30 gram on one side and 30 gram on the other side to have it symmetrical. And at this point here the glider stands at 270 grams and the hanged mass stands at 10 grams. So I'm going to have my first run. I bring the glider to my starting point and start the air supply. So I bring the glider to my starting position and let go. I immediately come here to hold this because I don't want it to hit here and break, safety first. So here I used gate modes and took 2 measurements. So I immediately record my measurements. And then I come back to the starting point. I reset the measurement and then I switch it to pulse mode and then run it again. Now I have all the necessary measurements in order to measure the acceleration of this object due to the mass that is 10 grams. Now in order to change the force, I will take some mass from this glider and add it to the hanging mass. The reason I'm doing this switch is because I want to keep the total mass constant in my system, so that I will cancel the effects of changing the mass and I will only deal with the force. So I come back again to my starting point and run the same experiment again. From gate mode, from the same starting position. Actually, immediately you can see as soon as I put more mass on this object, it started accelerating faster. So my time measurements will go down and down and down. Going back to the initial position to run in pulse mode so that I can determine the time it takes from this photogate to this photogate. And putting it in pulse mode, releasing it again. And as I suggested, the time it takes to travel from here to here will be shorter. So I can turn it off now. And now I'm going to do another mass change. Reset the equipment. Now I'm going to take another 20 grams from here and add it to here. Now in order to make it symmetrical, I'm going to do some changes because I want the mass on the glider to be symmetrical so that there is no shaking in between motions. Now I have 50 grams on this hanged mass, and I have 20 grams on the glider, which makes it a total of 240 grams coming to the starting point and running it all again, which is extremely faster. So I will record these values again for the velocity. To initial position and switching to the pulse mode from the same position. And again, I'm going to get a smaller value for the time it takes to travel from between photogates. Now to get the final set of values, I'm going to take all of the mass rings from the glider and put it on the hang here, and then reset all the values, and this is going to be the last set of data I'm going to get. Now at this point the hanged mass stands at 70 grams and the glider stands at 220 grams. Resetting again, putting it in gate mode for the velocity measurement and letting it go. Now this final value, which is going to be the with the maximum amount of force, so I'm going to get an even smaller value. And for the final time, coming to the starting position and putting it in pulse mode, releasing it from here, and I take my final time measurements. Now for the second part of this experiment, I'm going to keep the force constant. The way I'm going to do that is I will just put 10 grams of mass here, and I will not change it throughout the experiment so that the force that's coming from this mass will be constant throughout the experiment. And what I'm going to do is I'm going to change the mass on this glider. At this point I have extra 60 grams of mass here, so it makes 270 grams. And what I'm going to do, each run I'm going to decrease the mass and record my acceleration values. So for the first run, again, I'm coming to my starting position, resetting my equipment, setting it in gate mode to measure velocities, and turning on the air supply. Again, coming to my starting position, setting it in gate mode to measure velocities and just letting it go. Now I'm going to record these values. Now again I need to measure the time it takes between photogates. That's why I'm going to put it in pulse mode, reset the values, and do the same run again from the same starting position, and record the value. Now I will take 20 grams of the glider, so which make it 250 grams, and I will repeat the experiment. But what I expect, since the mass is decreasing, I will expect a faster acceleration. So let's run it and see. Setting it in gate mode. As I look at these values, I see that the time it takes for the glider to pass through one photogate is decreasing, which means the decreasing the mass is actually increasing the acceleration of the object. So let's go back and run it in pulse mode to see how long does it take between photogates now. And again, I see a decrease in the time it takes for the between photogates. So this means the acceleration is increasing. Now I'm going to take another 20 grams, but this time I want to make it again symmetrical. So I will just put 10 gram here, another 10 gram here, which makes it an additional 20 grams. Resetting, putting it in gate mode, turning on the air supply. Once it's ready, let's leave it. And again a slight decrease, which is going as I expected. Resetting to measure in pulse modes. And I can see from here again the time measurement decreases. Now for the last run, I'm going to take all of these mass rings off the glider. It's just 210 grams, the base weight of the base mass of the glider. Resetting for velocity measurement, putting it in gate mode, releasing. Yeah, the final value is also decreasing, so which means that my acceleration is increasing. Reset, pulse mode, again. Yeah, it's exactly as I expected. Now I can turn on the air supply and the photo gates. Now after this, all that remains is making some calculations and evaluating the results.
Now that we have concluded our experiment, all that remains is to use our data to find our results and interpret those results. Here I have the data table that I've gathered from the experiment. This column is the mass of the glider. This column is the hanged mass. These two columns are the measurements I took by using the gate mode in order to find the velocities at two different points. This column gives me the time it takes to travel in between photogates. This column will be the results of will be the acceleration results, and this column is the force applied by the hanged mass on the glider. Um, I have also copied and pasted the instructions that we have on our laboratory manual. If you like to go through them, you can just pause the video right here and to read them. And then otherwise, I will just go through my calculations. Also, as you can see, I'm using Microsoft Excel in order to perform my calculations. If you do not know how to make calculations with Excel, how to make graphs with Excel, this can also act as a tutorial for you. So let me just begin. Now I need to find velocities. In order to find velocities, what I'm going to do is divide the length of the glider by these time measurements. So for velocities at the first photogate, I will uh, divide 0.1, which was the length of the glider, 0.1 meter, meaning 10 centimeters, by the first time measurement. And I will get this value automatically. If I hold on this square dot and pull it downwards, it's going to give me the result for all these rows. This row is empty, that's why it's dividing by 0. I will just delete that and go to the second velocity measurements, which will be again 0.1 over, now this time, the time measurement from the second photogate, and pressing enter will give me the results. Again, I will delete this extra empty column, empty row, and now I'm going to calculate the acceleration from the second point here, which was given in our laboratory manual. The difference in velocities over the time it takes between photogates will give me the acceleration results. So I will find the difference in velocities by K4 minus J4 over I4. That was some sort of mistake. Now I can do this again. Over I4, which will give me the acceleration for my experiment. Again, deleting this. And the final calculations that I have to make is to find the force on the glider, and the way I'm going to do that is just using m times g. There's an extra a here, which let me delete that, and the applied force is m times g. It's equal to the applied hanged mass times g is 9.8 meters per second. Just making this calculations and deleting that. Now these are the measurements for my first part of the experiment. If you remember, in the first part, what I did was I decreased the um, mass on the glider. I added those masses to the hanged mass, and the reason for this, I wanted to keep the total mass constant. If you can see, 0.27 and 0.01 makes 0.28. Again, 0.28 total mass, 0.28 total mass, and again 0.28 total mass here. But the hanged mass is increasing, which means the applied force is increasing. On the second part, what I did was I decreased the mass on the glider, but kept the hanged mass constant, and by doing that, I kept the total force on the system constant. So from this part, I will get a mass versus acceleration measurement. From here, I got a force versus acceleration measurement. Now I can use this to make a graph to see how these parameters are changing the acceleration. So let me just go here and insert one chart. A scatter chart is what I'm looking for. Here, an empty chart. I'm going to right click on this and click select data. And from here, I can add my data to the chart. I press the 8. Series name from here, you can give it a title. At this point, I will skip that. Series X values. Now, X values are the values that I changed, right? So what I changed the force here. And Y values are the value that I observed. What I observed was the acceleration. So I select those and press OK, press OK again. And from here, if you can see, I have a linear increase here, which was actually what I expected, right? I expected that the acceleration to increase as I increase the amount of force I apply to my glider, so which kind of shows me that the original assumption was correct. Now I will move this chart to another page if I can. Move chart, new sheet, chart 1, yes. And from here I can also add some chart elements like some axis titles. Like from here, and I can work on this to make my chart look better. What I can also do, I can click on the data here, right click, add trend line, and I can see that this is a linear increase, which is what I was looking for. And without going further into that, I will go back and do some work on my second part of the experiment. And here, again, I will insert another graph. Again, I'm looking for a scatter graph here. And here, if I right click on this and say select data, add, and X values, here again, X values are what I changed. The value I changed was the mass in this part, and the value I observed, Y values, were the acceleration values here. And let's make it bigger by moving to another sheet. I'm just going to quickly write mass versus acceleration. And from here, it doesn't really look nice. So what I'm going to do, I'm going to work on the axis here to get some better, to make it bigger. Now, if I go into axis bounds, if I make the minimum 0.2, and for the vertical axis, let's click on the vertical axis here and make the minimum. Now I'm looking at here, make the minimum 3, which will look better. So what I was looking for here is to see that when the mass increases, the acceleration needs to decrease, right? Because I'm applying the same amount of force to a higher and higher mass. And as I see here, this column, this axis is the mass. As mass is increasing, the acceleration value is decreasing. However, here I'm not looking for a linear one. I'm looking for a sort of like 1 over x type of data. But since I have 4 data points, it will not be perfect, obviously. If I had gathered like hundreds of data, I would what I would see something like 1 over x, because it's inversely proportional to the mass. The acceleration is inversely proportional to the mass. So just by looking at these two charts, I can confirm that in fact the Newton's second law holds true while explaining the effects of force and mass on an object.